discuss this theorem. So in this theorem, we have a matrix space XD and A is a subset of X. So we have to prove these two statements. First of all, we will focus on the first part. That is, boundary point of A is nothing but boundary point of its complement. Getting? So that means set A and its complement, both of them are having same boundary. This thing we have to prove. So we have to prove that these two sets are equal. So obviously our regular method is we prove that first set is subset of other, and after that we prove that second set is subset of first set. So for that purpose, I am going to take one point from a first set and I will prove that it is in second set. Let us start. Let X belongs to deba A. That means X is a boundary point of A. That means X is boundary point of A. So you know that definition of boundary point says every open ball around X. I will show you here that thing. So suppose this is A, getting X is a boundary point. That means every open ball around X intersects A as well as its complement. So therefore, what can we say? Therefore, BXR intersects A, that means it is not equal to phi, and BXR intersects its complement also, that is not equal to phi, and this is true for every r greater than 0. After that, what will I do? I will simply interchange them. That means this thing I will write first, BXR intersection X minus A is not equal to phi, and this thing I will write later. So BXR intersection A is not equal to phi. This is true for every r greater than 0. My next step, I will simply copy paste. This thing I will write as it is. BXR intersection X minus A is not equal to phi, and BXR, see I'm making small changes here. What I'm doing, intersection X minus A not equal to phi for every r greater than 0. Maybe you are thinking what I have done exactly. See, X minus A, that means complement of A. But you know that if you take double complement, that means you will have original set. So complement of A is nothing but A itself. Getting? So that's why same thing I have written but in a different way. This is the only thing. See, did you notice anything? BXR intersects X minus A and BXR intersects complement of X minus A. So this is nothing but again definition of boundary point. As you can see here, if you say it is a boundary point of A, then we write A and we write X minus A. Same thing is happening here. Just we are taking X minus A and X minus A. That means what can we say? X is boundary point. X is boundary point of X minus A. Okay. So yeah, therefore X belongs to, symbolically we can write X belongs to dx, X minus A. Okay. So see, in this way we proved that means already we had taken X from boundary point of A, set of boundary point of A, and we have proved it is in set of boundary points of X minus A. So that's why this is subset of this one. So now we have to prove this is subset of this one. That means in a reverse way we have to prove. Exactly in a reverse way I will do it. I can do it. So that's why I will simply write implies and implied by. So in this way you can go in reverse way also. So therefore I will simply write our conclusion. Therefore this is subset of this one, this is subset of this one. So that's why both of them are same. Boundary point of A is nothing but boundary point, set of boundary points of X minus A. In this way we proved the first part. After that we will go for second. Before that you can make a screenshot of it. See, in part B also we have to prove that these two sets are equal. Boundary point of A is nothing but closure of A and closure of its complement. Whatever the intersection, that is nothing but its boundary. Getting? See, so here also I will do first set is subset of second set is subset of first. So that's why both of them are equal. So for that purpose I am taking one point y from d of A, deb of A. Okay, I will prove that it is in second set. So that's why we can say first set is subset of second set. I've taken y from deb of A. That means y is a boundary point of A. So why is a boundary point of A? So again we can use the definition. So definition says BXR, sorry, here I supposed to write Y since we have taken point Y. Intersection A is not equal to phi and BYR intersection X minus A, that is also not equal to phi for every R greater than 0. Getting? So the Y is a boundary point. That means every open ball around Y intersects A as well as its complement. Okay. So same thing I'm going to write but in a different way. So BYR intersects A not equal to phi for every R greater than 0, and here also I will write separately. So that means BYR intersection X minus A is not equal to phi again for every R greater than 0. Both things are true for any arbitrary R greater than 0. So that's why separately I wrote. Okay. So this definition, have you seen anywhere? Yes, this is definition of closure point. Getting na? So see, if you write minus singleton Y, then that is a definition of limit point. But see, if you don't have that thing, then it is a definition of closure point. So that's why Y belongs to closure of A. Getting? But here instead of A we have X minus A. So therefore what can I write? Y belongs to closure of X minus A. Okay, so these are definitions. Simply I followed the definition. See, and in set theory we replace and by intersection and we replace or by union. So that's why I can write Y belongs to A bar intersection X minus A bar. Yes, we got what we want. Getting? So Y belongs to this set. So we had taken Y from set of boundary points of A and finally we proved that Y is in this set. So that's why this is subset of this one. Now our task is to prove in a reverse way. Yes, exactly in a reverse way we can do it. So that's why simply I will write implies and implied by. So that means you can go exactly in a reverse way. So therefore, we proved this set is subset of this one, this set is subset of this one. So that's why both of them are equal. We can directly declare. So therefore, deb of A is equal to A bar intersection X minus A bar. So in this way we prove the second part also. You can make a screenshot of it. After that we will stop. Thank you. Bye bye.